8, 5, and 6 are vectors. Remember me giving you a heads up on vectors? It's called a directed line segment, meaning it is a line, but instead of the equation of the line, we have the vector, okay? And it represents the horizontal and the vertical. And then you have the diagonal, which is the vector, and it encompasses the horizontal direction and the vertical direction. If you look at this slide right here, this is where I just wanted to give you a couple of words, vocab words that are going to come up. You've got displacement, you've got velocity, you've got force. You're going to hear these words, and then I included examples of how they could be used, like how the word problem could start. How about we put you on a need to know? We will bring this back up as soon as we hit the first problem where you need to know it, okay? But it is right here that you can go back and reference it, look at it, and kind of wrap your mind around. Okay, so if I see an example talking about a 25-pound force required to lift the box upward, we're talking about force, which you should know because the word force is in there. Displacement's the one where they don't actually say the word displacement. For instance, a hiker follows a trail 5 miles to the west. They're not using the word displacement, but that is an example of a displacement vector problem. The good news is our word problems with vectors all involve triangles. Like, that's it, which means 3 sides. And they're going to give you 2 of them. You just have to find the 3rd one. Okay, so turn to this slide. This is where we're looking at the first vocab word, vector itself. It is a directed line segment. Look how I draw my line. My arrow in the end does not have the 2 arrows. I'm doing it as just one. That is your kind of like a notation that we're talking about a vector, not a traditional line, okay? 2 vectors are equivalent or equal if they have the same magnitude. Magnitude is the vector fancy word for length, and the same direction. Direction is the vector fancy word for slope. So take what you know about regular lines, traditional lines. If we found the length of a traditional line segment, we would use the, what formula? If I'm trying to find the length of it, do you remember from geometry? It starts with a D. If I just want the length of something, don't overthink it. If I need to walk to the nearest Starbucks, I need to know how far I'm walking. I would check the distance. There it is. Okay, so let's go back. Let me repeat the question now. So what I was saying is go to your traditional understanding of lines. If we have a line segment, and in the past I've said how long is the line segment, you would find the distance of it, right? Yes? Using the distance formula. Let's remind you what the distance formula looks like. Up here at the top, you've got it's the x-coordinates subtracted, the y-coordinates subtracted, then squared, then added together, and then of course you take the square root to undo any negatives well, there shouldn't be any negatives. You're undoing the squared, which took care of the negatives. So we'll say it again. Your traditional understanding of line segments. If I said, how long is this line segment, you would use the distance formula. Well, with vectors, I'm not going to say how long is the line segment. I'm going to say, what's the magnitude of it? Okay, magnitude, just think of in terms of what's the and I'm using my arms here because I'm hoping this will help you. What's the magnitude of the situation? So if I do that, I'm thinking to myself, like, how much are we talking about here? So magnitude means the length of it. And then if I say, what's the direction of the vector? Because it is a directed line segment, that is the equivalent of what's the slope of it. Okay? What's that phrase for slope that you might remember? Not slope intercept. Rise over run. Remember that? Now, the other new part in this problem is letting you know when you have a vector in front of you. Look at the directions. It says the vectors u, comma, or, comma, and w are shown in the figure below. Okay, first let me address this. This little bold u, lowercase u, is a vector. It's like the equivalent of if I had a graph with a line and I called it line L, right? Instead of line AB. You with me? So line AB is the same thing as line L. Okay, here, writing it as a lowercase bold letter is the same thing as calling it line L, and then writing it as vector OR is the same thing as if I called it line AB. Okay? When you're using the two letters to name a vector, order does matter, just like when you were naming a ray in geometry. Ray A, B means it starts at A and then it passes through B. Remember that from geometry? Vectors are the same way. It says vector OR. That means it starts at O and then it travels to the direction where R is located. You with me? Okay, so we have three vectors on this picture right here. It says show that U equals vector OR equals vector W. This is a way of saying show me that the length of U matches the length of OR matches the length of W, and show me that they have the same slope. Okay? So we're going to do this 3 times with the length, then 3 times with the slope. So there's a lot to write here. So let's organize it. First, let's write that we're dealing with the magnitude. Magnitude right here. Title it. So you know when you're looking back at your work, remember magnitude just means the length of it. Let's find the magnitude of vector U first. So let's apply the distance formula. Vector U is 2, 4 to negative 1, 3. We have the distance formula right here. Everything's the same, just like geometry. So I'm going to plug it in, square root. Does not matter how you subtract your x's or your y's, because once you subtract them, then they get squared. So it doesn't matter how you subtract them. They're going to get squared. So any negative is going to become positive. So don't worry about trying to nail down the sub 2, sub 1s. Don't worry about that. I just focus on looking at the line. So I tell myself, so I've got 2 and negative 1 are my x's, right? So 2 minus negative 1 squared. Then I've got 4 and 3. 4 minus 3 squared. Now we've talked about what? No, that's you. That's you. Now you're going to go to your calculator and you're going to type just the radicand part. Don't type that giant square root on the outside, just in case it's ugly. type just the part under the radicand. Let's get out of polar mode before it messes up my sophomores. Hit mode, go back to function mode. Alright, we're going to type just the radicand. So parentheses 2 minus -1, close parentheses squared, plus 4 minus 3, close parentheses squared. So, 3 is positive. So the part under the radicand is a 10. You do need to write the square root because it was there. And then now we're going to repeat this process with OR and with W, and we're going to confirm if we come to square root 10. Okay? So now we're going to do vector OR. So focus on the coordinates O and the coordinates for R. Subtract the x's. And it really, right here, I'm going to actually subtract in the other direction because then I'm subtracting nothing, right? If I do, so -3 minus 0 squared plus -1 minus 0 squared. When you go to your calculator and type that in, you should confirm that it is square root 10. Well, 10 in your calculator, but then on your paper it'll be square root 10. Now we're going to repeat with vector W. Once again, it does not matter which ones you label as sub 2 or sub 1. It doesn't even matter if you're consistent here. Some formulas you have to be consistent, but with distance formula it doesn't matter because they're going to get subtracted, then they're going to get squared, and then they get added together. But you should see that you get 10 under the radicand, or under the radical, so you have square root 10. You need to know that there's two parts to showing vectors are equal, and it's written right here. There's two parts. You want to take notes for yourself for practice problems. You have to show ... one same magnitude. Second part is same direction. Well, the magnitude comes from the distance formula, and then the direction comes from the slope. So now we're going to go back to your understanding from geometry and algebra 1 with slope. Let's remind you, the slope formula, I'm going to write it, I'll write it up here since we put the distance formula up there. So slope is, take the y's and subtract it over the x's and subtract it. Now with slope, order matters. Order matters. And what we mean by that is however you subtract the y's on the top of the fraction dictates how you have to subtract the x's in the bottom of the fraction, or you'll get the wrong answer. Okay? So we're going to repeat. Now we're going to find, let's use the new vocab words. We're going to find the direction of all three vectors. Let's start with U. I'm going to just put, do y'all remember the notation for slope? Okay, no big deal. I don't want to introduce, it's M, but I don't want to introduce it and throw you off and make you think it's a fourth vector or something. So I'm just going to put a U here to say I'm looking at U, and then I'm going to put a colon. All right, I'm looking at the slope for U. However you subtract the y's dictates how you subtract the x's. So if I go from original point, when I say original, I mean like the starting end of the vector, right? Because there's no arrow there. So if I go from here, if I start here and then subtract this with my y's, then I have to do it that same order with my x's. Okay, so with the y's, it would be 4 minus 3 over 2 minus negative 1. Then you can type that in your calculator in fraction form, and it will leave it as a fraction, or you can do it in your head. 4 minus 3 is 1. 2 minus negative 1 means add, so it's 3. So this has a slope of 1/3. Which makes sense, because if you had a grid here, which we don't have a grid, we could count rise over run. It rises 1, and then it runs 3 to the right. Right? So you actually, if you create that grid, you can confirm that with the other vectors. Let's do the slope of OR. So this is my, well, in this case, my original end is 0, 0, and my the other end is both negative. So this is where you have that freedom of choice of you can subtract in the other direction as long as you do it with both of them. I'm going to subtract from this number to this number because then I'm just subtracting nothing, right? But it doesn't matter as long as you're consistent. All right, y's first. Negative 1 minus 0 over x's. Negative 3 minus 0. So negative 1 over negative 3 becomes what? Positive 1/3. All right, let's do W. I'm running out of room. I'm going to put W right here. So, doesn't matter here. I'm going to go from that end to this end. So, negative 1 minus negative 2, the y's, over the x's. So negative 1 plus 2 is 1, 4 minus 1 is 3, and now we can see that all of them have the same magnitude, all of them have the same direction, so therefore you can say that all 3 vectors are equivalent. Let me show you the visual of what that means. Look at this slide right here. Look at the slide, the picture at the top. This is what vectors of the same magnitude and direction look like. Look at the 3 down here at the bottom. Notice the one in the middle, you might think, why is that not also the same? The arrow's in opposite directions, so they have different directions. So that slide is there to help you wrap your mind around the visual of what it means by equivalent versus not equivalent. Okay?